Stand on a coastline during the middle of the day, and you will almost always feel a steady breeze blowing in from the ocean. Stay on that beach after the sun goes down, and you will notice a distinct shift. The wind reverses direction, blowing away from the shore and out toward the open sea. The air isn't being pushed by a storm or a distant weather front. A hidden thermal engine is turning on, running in one direction and then running in reverse. For any transfer of heat to take place in the universe, there must be a strict temperature difference between two isolated systems. Energy will always attempt to flow from the hotter system to the colder one. When you grab a hot frying pan, that heat transfers directly through the solid metal into your hand. The molecules in the handle vibrate faster, but they remain stationary. The mechanism driving the coastal winds works differently. It requires the actual matter itself to physically travel across space. This animation illustrates the concept of convection. Convection is a mode of heat transfer driven entirely by the bulk transport of a fluid from one location to another. Because it requires actual physical movement, this mechanism occurs only in liquids and in gases. Their molecules are loosely bound and free to travel across physical space. Instead of energy passing through a material, the fluid itself acts as an active vehicle, carrying thermal energy along with it. This physical transport provides the solution to the shifting winds on the beach. During a sunny day, the sand on a beach absorbs solar radiation and heats up rapidly, while the ocean remains relatively cool. This happens because water has a much higher specific heat capacity than dry land. Specific heat capacity is a metric that defines how much energy is required to raise the temperature of a specific amount of a substance. As the ground bakes, the atmospheric air sitting in direct physical contact with hot sand begins to absorb that heat. In this cross-section, heated air directly above the sand expands, dropping in density. Being less dense, buoyancy takes over, and this hotter air rises vertically. This creates a low-pressure void over the land. To fill it, cooler ocean air immediately rushes horizontally across the beach. The hot air rises, and the cool air rushes in to replace it. This continuous loop of moving fluid creates the daytime sea breeze. As daylight fades, the thermal dynamics invert. The ground rapidly bleeds off the heat it accumulated during the day. The deep volume of the ocean, however, holds on to its thermal energy much longer. The temperature differential has now flipped. The surface of the water is physically warmer than the adjacent landmass. In this nighttime diagram, the convection cycle runs in reverse. Air over the warm water expands and rises vertically. The void is now over the ocean. Cooler, denser air from the land flows out to sea to fill this zone, creating the nocturnal land breeze. Gravity, density, and buoyancy govern this entire process. Because it relies entirely on natural environmental differences to move the fluid, physicists classify this specific mechanism as natural convection. Natural convection relies on gravity acting upon fluids of different densities, but fluids can also be compelled to move by external physical forces. When an external device drives the movement of a fluid to transfer heat, the process is called forced convection. Inside an automobile engine, a mechanical water pump rapidly circulates liquid coolant around the hot cylinders. The moving fluid constantly absorbs heat and transports it to the radiator, preventing the metal from melting. In a typical home heating system, a motorized fan forces warm air through a network of ducts, physically pushing the heat into separate rooms to maintain a steady temperature. Biology utilizes this exact same mechanical engineering. The human heart acts as a powerful pump, driving dense fluid through miles of pressurized vessels. Blood circulation is an internal forced convection system. By constantly moving fluid from the hot interior to the cooler extremities, the body maintains a uniform 37 degrees Celsius temperature. Whether fluid is drawn upward passively by buoyancy or pushed forcefully by a pumping mechanism, moving matter to distribute heat is a universal method for stabilizing extreme temperatures. These same thermal properties operate far beyond microclimates and biology. They govern the movement of the entire Earth's atmosphere. The planet has a massive thermal imbalance. The surface at the equator receives intense, direct solar radiation daily. The poles receive highly diffused sunlight and remain frozen. This diagram shows the theoretical outcome. Superheated equatorial air expands and rises, creating a massive void. Driven by buoyancy, it moves outward. Reaching the freezing poles, it cools, descends, and streams back along the surface to fill the original equatorial void. If the Earth were perfectly stationary, this single enormous convection cell would uniformly dictate the weather across the entire planet. The Earth is not stationary. It is a rapidly rotating sphere, and that rotation disrupts the simple thermal current. Because of the planet's spin, the rising air at the equator has an eastward speed of roughly 1,600 kilometers per hour. The air at the poles has an eastward speed of 0. Watch how rotation modifies this. Extreme eastward momentum prevents equatorial air from reaching the poles. Instead, it cools and descends prematurely at 30 degrees latitude. Highlighted arrows show this air forced back along the surface to the equator, creating the trade winds. Heat requires matter to move, from blood pumping through arteries to the evening ocean breeze to the massive planetary winds that drove global navigation. Moving fluid is the mechanism the universe uses to find balance.